Hello, everyone. So let's start collections. Now, the way that I'm going to approach this is from the perspective of C++. And the reason behind that is that the support of collections or the support for data structures that we have in C++ is totally unmatched. There is no such support available in any language, including Java and Python. So what I'll do is that I'll start from, you know, I'll start from the C++ perspective of how standard template library defines particular data structures, and then I'll switch perspectives between Java and Python. So in C++, we have basically four different types or four different um, anatomies of data structures. So the first type of data structures are what they call as sequence containers. Now, these data structures obviously, by name suggest that, they have specific sequence, they have specific order, okay? And in, there are like five basic types of structures. So first one is an array. Now, what C++ calls an array is any data structure that is contiguously located in your memory, and you have to define its size beforehand. So if you know that my array is going to be 1,000 elements, then I should define it as a contiguous array that is allocated memory in stack. Okay, so we have different types of different levels of memory that a program can access, and the fastest, well, not the fastest, but at least the second, the third fastest level from C++ perspective is the stack. Okay, so every method has some memory allocated in stack, and that memory is fixed basically. So if you know beforehand that this is the size of my array, it is always better to use stack, because the memory access and processing is faster. In Java and in Python, unfortunately, since they are runtime interpreted languages, there is no such thing as stack. Although in Java, recent versions uh, try to monkey patch this approach, but in all fairness, the stack allocation in C++ is what makes it really fast. And so if you know your size of array beforehand, it's better to allocate memory in stack. So therefore, they have the specific data structure for that, which is not available in Java and Python, because language doesn't support compilation. There's no stack of memory in Java and in Python. The second, if you want to allocate, items at runtime, but those items are contiguously located, then it's in the C++ variant is called as vector. The Java variant that runs on heap is array list. In Python, we call it as a simple list. But then again, the difference is that this Python list is dynamic. You can have a heterogeneous array that contains integers, floats, and whatnot. Array list and vector, they are they are strongly typed, so you have to explicitly say that this is array list of some particular object of some particular data. You cannot have heterogeneous array list or vectors, whereas you can have heterogeneous lists in Python. Now, the difference between array and a vector is that one exists on stack. The array data structure exists on stack, and vector exists in heap. Okay, so this is the only difference. Then you can also have this second structure. Imagine that you have a vector. When I say a vector, I mean that the structure which has contiguous memory location, contiguous locations that are allocated for each item, but then the insertion or deletion takes place only from one end. Okay, in DQ, this constraint is relaxed, so you can insert at both ends, and you can also delete. So the DQ or the deck, it shrinks from both sides, and it also expands from both sides. The Java data structure is called as array DQ. There is no such structure in Python that does that. In fact, what Python says dequeue is what is actually a doubly linked list in C++. Okay. So if we talk about linked list, then what this means is that we can have we can have items spread across different locations in your heap memory, and they are located either by by this double way connections or single way connections. So if you have a double two-way connection between each item, it is called as a doubly linked list. If it's just a single way connection, then standard template library calls it forward list. There is no such forward list in Java. And the Java community will say, oh, just take simply linked list and just don't use the second way communication. But C++ has a separate structure for that. In Python, what they call as dequeue is basically a doubly linked list, okay, in terms of inherent representation of data structure. Now, all of these are sequence containers, okay, which means that there is a specific order. There is, one item 3 is located after 45 or, before 1, for example. So there is a specific sequence of these individual items. Then we have what we call as, unordered associative containers. And what this means is that, the items in this case do not, have a strict order of between them, okay? So, and internally what happens is that they are internally represented in terms of hash maps. And the good thing about those hash maps is that, if you have to, let's say, if you have to search a particular element in any of these containers, you have to traverse through each of through each item, okay? So this means that searching is linear in terms of its time complexity. So it's order of n if you have to search any number in any of these sequence data structures, okay? But here, the searching is basically a constant type operation. You just, so internally what hash maps do is basically every item has some unique hash code. And once you are looking for, specific item, you just check that, whether or not that hash code exist in that data structure or not, okay? So it's like, if you can calculate a hash code, which is basically, just a procedure of, like, the hash code and you want to see, which index does this hash code correspond to, this just takes, a constant time. So, you don't have to go and check, each element one by one. You just, look for the hash code. If it's there, then your element is there. So everything, including adding new element, including searching for a new element, is constant time. And so therefore, this is what, makes these associative, unordered associative containers, very fast in terms of data manipulation. So what we have here is, for example, there are two types of objects. One is called, hash maps, or in Pythonic terms, they are called as dictionaries, and the second ones are, sets. But internally, both of these objects are the same. So imagine if you are coming from a Pythonic background, you know that dictionaries have key value pairs, okay? You have some key and some value associated to that key. But if you think about it, if I take the list of those keys, that list of keys is basically what we call as sets in Python, okay? So what you call in Python as sets is basically nothing but, a collection of unique unordered items. And what they are internally, how they are, manipulated or represented internally is basically a dictionary which has no value, which has just simple keys, okay? So in sets, you don't have explicit access to your values. You just have explicit access of keys, and you call it as a set. But internally, you can visually or pictorially imagine that sets are just dictionaries without having explicit access to your values. But in C++, what we have is basically you can have two types of sets. One which where you have this assertion that the keys should be unique, okay? But then you can also have those sets which implement constant time searching and constant time insertion and deletion, but where you can have multiple keys having the same value. So this makes obviously the the operations are not as fast, especially if the keys are duplicated. Then you need to figure out how to resolve conflicts, but at least the structure is there. In Java, you have hash set, which are basically similar to what sets are in Python. But both of these hash sets in Java and sets in Python have this constraint that your keys have to be unique. There is no such constraint. In fact, C++ have a separate data structure which relaxes that constraint. Then in C++, you have this maps. Once again, you can have maps which are hashed by unique keys, or multi-maps which do not have this restriction. There is no such cases in Java and Python where you can have hash maps implementing non-unique keys in some sense. But so both sets and hash maps, they are unordered. You cannot say that, okay, this NIC, for example, our NIC national identity card number is unique. You cannot say that this unique number comes after that. Okay, so there is no order of things. All of that order is determined by there is no order. In fact, the index is determined by hash key of each element. And then C++ can say that, okay, what if I take these four data structures and enforce a particular order to these individual items? And this forms associative containers in standard template library. So imagine that if you have a unordered set, but now you say that, okay, I'm going to sort that unordered set with respect to their keys. Internally, what happens is that we have a binary search tree which we use to represent which item comes after which item. Okay, so if you just take these unordered associative containers and you enforce a particular constraint that, okay, now these these data structures will be ordered via keys, okay, whatever that means. But in Java, you can also have tree set or a tree map, a hash set that has a particular order, and this is also something unique. So you don't need to sort those, like you don't need to order your set by your keys. You can have custom comparator. It depends upon you how you want to sort those keys. Okay, but in any case, that the data structure itself has some order of individual items, and it depends upon you how you would define that order in Java. In C++, you can also do that, but by default, the method is it sorts by keys. I think in Java it's also tree sets and tree maps. The order is by ascending order of the keys themselves. In Python, we don't have in Python, we don't really see that how can a set or a dictionary have a particular order. By definition, this order of hash keys doesn't make sense to Python, but it really is important, because if you have a particular order, then you can search. If you have let's say if you have a tree, a binary tree, where each element has let's say a couple of children, then you can search in logarithmic time. The searching of a particular item is order of log n in terms of its computational complexity. We'll see it maybe later. So these are called associative containers, where you enforce some order. And then, C++ community will say that, okay, what they call as a stack. So a stack is basically, a data structure that behaves like a basket. If you have a basket or a bowl that is open from one end, C++ will refer, such data structure as a sort of container adapter. And what this means is that it adapts your sequential container. So we saw that, sequential containers are these five, you know, data structures that have particular sequence to themselves. And then you can say that, okay, a stack is basically, a basket. How will I implement that basket depends upon myself, whether that basket internally is represented as a vector, or internally is represented as a DQ, or internally is represented, as a linked list. So, a basket can contain 100 items. It depends upon how you see your items, being related. It's just that, so you can have a doubly linked list as well. You can have a DQ as well. You can have a vector as well, as long as you only insert, from the top, and also add it from the top. That is a stack for C++, which is a very nice idea. A stack can implement any sequential container which is either a vector, a DQ, or a list. Um, in Java, I don't think that is the case. You have a particular stack, and I think internally, it is just, an implementation of array list. Although I will see that, how is that the case, but I don't think you can have multiple. Like, you cannot simply say that, okay, a stack is an implementation of any of these three. But I'll come back to you. Right now I'm not sure that how is this stack structure internally implemented. But at least in C++, it is explicit. You can choose any of these three structures to represent your stack. A queue is, once again, there are 100 persons, lined up in a queue. Obviously, you can have addition and insertion or deletion from both ends. It depends upon your queue, how those 100 persons are related, whether those 100 persons exist on a contiguous memory location, or maybe they are separated and, linked via doubly linked list. So it depends upon you, how, like, what are the internal connections between each of those 100, members. It depends upon you. Both of list, doubly linked list, or a DQ behaves like a queue. Obviously, vector cannot be represented as a queue, because, vector has insertion and deletion only implemented from one end. Okay, whereas a queue, you are supposed to do this insertion and deletion from both ends. And likewise, a priority queue internally is represented both as a DQ or as a vector. A priority queue is something that, you compare which item is, like, the insertion and deletion depends upon some value associated or some rank associated to each of these items. And so internally, doubly linked list is not represented, because, if you have a doubly linked list, if you have to insert, or let's say access a particular location, you have to traverse, you have to jump, so it's a linear time operation. But in priority queue, we don't want that. If we don't want to, we want to have indexed, we want to access every element, in constant time. So that is why, doubly linked lists are not supported as an underlying container of priority queues. In Java, we also have priority queues. Once again, I'm not sure how they are, what sort of data structure internally is used within the priority queue. In Python, we don't have any representation for stack or queue. There exists in collection interface this heap queue interface, which which represent a binary, which uses a binary tree to represent your items. Okay. So this concludes, in some sense, a brief introduction of different types of data structures that we have available in C++ versus Java versus Python.